And we are live. Okay, so someone, as promised, has had her visit with the hairdresser, and she's very sleek and smooth, and I can see her eyes. But she's also been outdoors all day today. Oh, lie down, lie down. Go to sleep. She needs to sleep. It's already past supper, so she's not sitting there waiting for supper like she often is when I'm making these videos. She's eaten, and she's had a lot of exercise. It's time for her to get a snooze. And I've been outside too, doing a lot of yard work, building a fence, things like that. It was fun. But now for the math. I'm wearing my Tottenham Hotspur jersey. That is soccer team from London, of course. And this week we are still doing geometry. But we're doing surface area. So we have been doing geometry of two-dimensional shapes for a couple of weeks now. So two-dimensional shapes, what does that mean? They're the shapes that we have been covering: the square, the rectangle, the triangle, the trapezoid, the circle, and the parallelogram. These are all two-dimensional shapes. They're very easy to draw. In fact, I'll draw a rectangle really quickly. Okay, let's see if I can do fairly well without using a ruler or a protractor. Drawing a two-dimensional shape is easy because I'm drawing on a two-dimensional surface. I'm drawing on a flat surface, but it's easy to draw a rectangle and have it look like a rectangle. A three-dimensional shape is an object that has depth. It is a solid shape, like this one, for instance. This is a rectangular prism. It has faces that are rectangles. There are 6 faces on this thing, and all of them are rectangles. Not quite so easy to draw because, reminder, I'm still drawing on a two-dimensional surface. So I'm trying to draw a three-dimensional shape on a two-dimensional surface, and that presents all sorts of interesting challenges. I can do this. I can draw angles. I can draw lines going at an angle, and if I keep using the same angle and keeping the lines the same length, I'm able to very quickly put together a two-dimensional drawing of a three-dimensional object. And it looks like a rectangular prism. It looks kind of like that one I held up, which is actually a box of staples. But it'll look even better if I also draw, and I like using dotted lines for this. Now it looks even better. So this is part of geometry, is the representation of three-dimensional solid objects with two-dimensional drawings. And this has to happen a lot, because this could be, for instance, a box. In a word problem, the word problem presents you with a box and starts asking you questions like to calculate how much cardboard it would take to make a box of that size, that sort of thing. And in order to do that, the question will often provide you with a diagram of the shape that the question is about. And then you have that same old challenge, which is representing a three-dimensional object with a two-dimensional drawing. Well, this is one of the ways of doing it, and it's not the only way of doing it. We have the net drawing. Okay, I'm going to get right into my net drawings. I did a couple of them today. I'm quite proud of them. They took a bit of time. I highly recommend that math students try drawing things like this. So what I have here is a net drawing, often referred to just as a net. And this one is of a cube, because if I were to cut this out and then fold on all of these lines, I would be able to fold this together and it would form a cube. Why would it form a cube? Because a cube is a three-dimensional object that has 6 equal faces that are all squares. They're all squares the same size. So I drew 6 squares the same size when I made this. Of course, I also put in these little tabs so that if I do cut it out, I have a bit of extra paper to fold over so that I can glue it together or staple it together or attach it together, whichever way. Well, the way that I decided I wanted to do that was with glue, and this is the result. A little bit squishy and wonky, but what I did was I made 2 copies of this net drawing, and one of them I left on the paper for you to see like this, and the other one I cut out and I glued. You can even see the tabs. You can see they're all wrinkly because of the glue that I used. But I managed to represent a three-dimensional object with a two-dimensional drawing. And that's going to be back and forth. It is 3D, we know it's 3D, but we're looking at a piece of paper which is 2D. That challenge keeps on coming back. So I am very proud of my net drawing. And one of the things that we can do is we can find surface area by finding the areas of all of the faces of the three-dimensional object and adding them together. So let's start, well, I'm going to start with this. This is a rectangular prism. And I have to give it some dimensions. We have nothing to work with. What I can do actually though is I can measure it. I'll give it dimensions, I'll give it its real dimensions by measuring it in inches, maybe with a bit of rounding. I don't want to have all sorts of decimals and fractions, etc. That is 6 inches. That happened quite nicely by itself. And this is 11 inches. And then this is the one I haven't measured yet. I'm going to call that 4 inches. So the worst part of my drawing is this corner over here. That's not really where it belongs. I should sort of mess around with it and make it look better. But we now have a box. So it's kind of like this little box of staples, but it's bigger because 6 inches by 11 inches by 4 inches is quite a bit bigger box than this one I have in my hand. How are we going to find the area? Well, all of these faces are rectangles. None of them are squares. The 4, the 11, and 6 are all different, so we have 6 rectangles. But 2 of the rectangles that are opposite faces are going to have the same area. Again, working very similar to this. This particular area, if I twirl this around, is going to be equal to this area that is on the opposite face. And that keeps happening. So, this face here that I'll shade right now has, let's say, it's a rectangle. So the area of a rectangle formula is base times height. And it has a base of 4 inches. But its height will be the 6 inches. And therefore we have 24 square inches for the area of that face. But there are 2. There's the one I shaded and this one over here, which I can also shade. Okay, so I have 2, but they're going to be equal to each other. So I'm just going to say times 2 equals 48 square inches. We're on our way to finding the surface area of this three-dimensional shape, which is the area of all the faces added together. But I've only done 2 of the faces so far. I have to keep going. Area of a rectangle equals base times height. How about if the 11 inches is the base and the 6 inches is still the height? So we have 11 times 6 equals 66 square inches. But there are 2 of those faces as well. The one in the front here and the one in the back. The way I drew it, that's the way I'm visualizing it. So times 2 equals 132 square inches. We're nearly there. We have 2 faces here, 2 faces there. We need the last 2 faces. The last 2 faces are going to be the 4 by 11. 4 inch and 11 inch, and that's a little bit harder to visualize, but that's the bottom and the top. So the bottom and the top are also rectangles. They still have the same area formula. And which one we call the base and which the height between the 11 and the 4, well, it's a toss-up, so we can do it either way. I'm going to say 11 inches is my base and 4 inches is my height. So I have 44 square inches, but there are 2 of those as well, the top and the bottom. Need more chalk. Times 2 equals 88 square inches. Okay, we have the areas of all 6 faces. A 24, another 24, a 44, another 44, a 66, another 66. If we add together all 6, we are going to have 132 plus 88 plus 48, which is 132, 140, 220, 268 square inches. We have found the surface area of a three-dimensional shape. This box, this rectangular prism, which has a bottom that is 11 by 4 inches, but it has these front and back sides that are 6 by 11 inches, and then we have the sides over on the ends that are 4 by 6 inches, and we're able to add it all together. So it seems like an awful lot that we've done, but it isn't hard. because all of the faces were rectangles, and we've been working for quite a while at finding the area of shapes like rectangles. So being able to piece those together is useful. Okay, that shape I'm done. Now I'm going to find the real surface area of this cube. And the cube, of course, the cube is a rectangular prism. What makes this a rectangular prism? The base is a rectangle. And the top is another rectangle the same size. When you have a shape where the face on the bottom is the same size and same shape as the face on the top, that is a prism. And there are different types of prism depending on what the shape is on the bottom. You can have a triangular prism where the shape on the bottom and the top is a triangle. Those two triangles will have equal areas. But a cube is also a prism because the shape on the bottom is a square, and a square is a special type of rectangle. And the shape on the top is another square the same size. So this is also a prism, but we tend not to call it a square prism. We tend to call it a cube. We use them so often and for so many different things because, of course, they are so useful that we have a special name just for this three-dimensional shape, the cube. Okay, let me erase, and then let me find the surface area, the total area of the 6 faces of that cube. And I happen to remember how long the lines were that I drew on the net drawing, and that's going to help us to find the areas that we need. But with the cube, it's a little bit more straightforward because all 6 of the faces are equal. So if I find one of them, then I have all of them that I need. I can add the 6 faces together, or I can multiply the area of that face by 6. So the area was the side length of the cube. Let me see if I can draw the cube. No. That's not too bad. For a freehand drawing, I guess that's pretty good. Okay, so the side length of the cube that I made my net drawing of is 2.5 inches. And why? Why did I choose to make it 2.5 inches? Because I wanted it all to fit on a piece of paper. And this piece of paper is 8.5 inches by 11 inches. So 4 times 2.5 is 10. That fits with an 11. I couldn't make it much bigger. It wouldn't have fit. So I just drew 6 squares, and they're equal to each other in their area. All of these squares, all of them have the same side length. And then I drew extra little tabs so that I could glue it all together. Okay. So the area of a square is side length squared. And the side length of this particular square is 2.5 inches. So the area is 2.5 squared. And that is 6.25 square inches. But that's just one. The other 5 faces are equal to this one. So I can say, okay, times 6 equals, that's 37.5 square inches. And you can see how straightforward the cube is to work with, because for the same reason that squares are fairly straightforward to work with, things become simple when all of the dimensions are the same. So we can do the surface area of a cube, and we know it's kind of easy, but we also successfully found the surface area of that rectangular prism. And we can do this with any of the shapes that we need to. Okay, how about a triangular prism? No, not a triangle. I'm not doing a triangular prism yet. I'm going to do a triangular pyramid. Actually, that's something that's worth talking about. So we've talked about what a prism is. The base has to be the same size as the top. So a triangular prism, I'm going to get a diagram of one up on my computer screen so that I can hopefully, yes, here's a good one. So I can just draw a triangle. It can be an equilateral triangle. This one looks like it might be quite close to being equilateral, but it doesn't have to be an equilateral triangle. And then, how will I do this? I'll draw another triangle over here, but I'm making sure it's the same size as the first one. And then if I connect, and I'm going to use dotted lines there, I managed to draw a triangular prism. So even though I didn't make the triangle lie on the bottom the way I happen to have drawn this, you can imagine this shape tilting so that you could tip it over so that the triangle is on the bottom, and then you can see that the triangle on the bottom will be the same size as the triangle on the top, and that makes it a prism. And that is part of the challenge of dealing with prisms, is that they're not always drawn for you so that the bases are looking like they're on the bottom. So you have to sort of do a visual impression of it in your head and maybe sort of spin it around, tip it over in your head. And that is called visual and spatial orientation, and it's an important skill for people who are studying geometry. There's my triangular prism, but I also want to show a triangle pyramid. So what's that going to look like? Again, I want to get one to use as a model. So there's two of the sides of my triangle. Because the third side is going to be in the back of the figure, I'm drawing it with a dotted line. And then I need to go up to this point at the top of the pyramid, which is called the apex. So similarities and differences. A triangular prism has some things in common with a triangular pyramid, but there are some things they very much don't have in common. This has 4 faces, which are all triangles. And this one has 1, 2, 3, 4, 5 faces, which can be kind of tricky to see, which 2 of which are triangles and the other 3 are going to be rectangles. So just listing the differences and similarities between the triangular prism and the triangular pyramid is useful, because it sort of allows us to get it straight in our heads what it is that we're dealing with when we deal with these 3-dimensional shapes. You can see that there's so much more variety and so many more things that you can do. Just think of the word problems we could come up with, all these different things, because the 2-dimensional shape is so straightforward compared to the 3-dimensional shape. There's so much more to it. Okay, so I like that. I'm going to show you my net drawing of that's kind of a net drawing of a shape much like this one. I drew a triangular pyramid net where all of the 4 faces are equilateral triangles. And I also drew the extra little tabs so that I'd be able to cut it out and fold it together and make the 3-dimensional shape to show you as well, which I did. So there it is. And you can see some of the tabs. And I managed to do that. So this is a nice little math lab. It's a great thing for students to do. There are so many more shapes that we could do. I did 2, but there are many more. In fact, just when you think of all the different sizes and shapes of rectangular prism, there's a lot of different shapes that you could do. Drawing them has its own challenges, but what are we doing? We're drawing rectangles, or we're drawing triangles. For a rectangular prism, you're drawing rectangles. But then we're making sure that the net really could fold together to make the shape. And so that presents challenges of its own. I highly recommend that students experiment with this. It was a lot of fun, and I would have liked to have spent a lot more time doing it, but I also wanted to be able to get to the chalkboard wall and, find some surface areas and do some calculations. Let me see what I have not covered yet. Okay, so the prism can have a triangle as the base, but it can also have a rectangle or a square as the base. We've talked about all of those. And any other 2-dimensional shape could be the base of a prism as well. So something like a trapezoid or a parallelogram, a pentagon, anything can be a prism so long as that 2-dimensional shape that is the base has an opposite face that is the same shape, the same size. Then you have a prism. And there are an awful lot of different ways that we can do this. Okay, what's next on my list? Talked about the pyramid, we talked about the apex. I'm glad I have covered that. A face is a flat surface. We have some of the lingo that we reuse from our 2-dimensional geometry, like the vertex. We talk about the vertex of an angle, or the vertex at the corners of a 2-dimensional shape, like a rectangle or a triangle. Well, with the 3-dimensional figure, we still refer to it as the vertex. But notice how, for instance, this one here, I'm trying to hold it so you can see 3 faces at once. This vertex here actually has 3 edges that meet there. 1, 2, and 3. Instead of just 2. And so again, that's all part of the transformation from 2-dimensional geometry to 3-dimensional geometry. Interesting stuff. And then there's the sphere. I had to get around to talking about the sphere eventually. Okay, so what's a sphere? A sphere is a ball. You often would just want to call it a ball, but a sphere is this shape, doesn't have any faces. Spheres are interesting. They're also very useful. I have no idea what this ball is for. It's not a street hockey ball, because this is a street hockey ball, and it's actually a little bigger. The orange one is a little bigger than the green one, so I just don't remember where I got this green ball. And then we have this lawn bowling ball, which is a little larger again. And then we have my granddaughter's soccer ball, which is quite old. I gave it to her when she was 2, and she is now 9. It's still kicking around in our backyard. Dirty though. And I have this basketball. Nice old basketball that was once very nice to look at and is now kind of worn out. Still works. Okay, so how about the surface area of a sphere? We can't find the area of a face and add the areas of faces together because the sphere doesn't have a face. We have to use a formula for the surface area of a sphere, and I think I want to use that formula for all 5 of those. Since it's the same formula, we're doing it 5 times, we will see a lot of repetition. So what is the formula for the surface area of a sphere? I wrote it down, there it is. 4 pi r squared. And there's that pi again that we're used to from dealing with the circle. Well, the sphere, it looks like a circle if you don't see the depth of it. And so pi is involved. And then there's the radius. So the radius, much like the radius of a circle, the radius of a circle is that distance from the center of the circle to the edge of the circle in any direction. Well, the radius of a sphere works the same way. It's just that I can't actually see the very center of this lawn bowling ball right now, but I know that there is going to be a point in the center of this ball that is equally distant from any point on the surface of the ball. And that center, if I draw a straight line from that center to the outside surface, is going to be a radius. So very similar to that of the circle. Now, how do I make a circle look like a sphere? I can only think of 2 ways. So I'm just sort of smudging, getting rid of that radius. One way is to sort of do this sort of little trick where you put kind of a reflection as if it's shiny, and that kind of helps give it that 3D look. And then another way, of course, is to give it a shadow. And I'm doing okay. I'm going to walk over to where you are and say, okay, that is not the best sphere I have ever drawn, but it still looks a little bit more 3-dimensional than the circle that I started with. So there, I'm going to erase that and not try to draw one again in this lesson. But we are going to use the formula. And I had to find the radius for all 5 of those balls. So I'm going to use this formula 5 times. I guess I'll say the area of the green one. I'll start with the green one because it's the smallest one. So we'll go from the smallest to the largest. The radius of this is 1 inch. 4 pi r squared, 4 times pi, which we're going to use 3.14 like we're used to, and then r squared is 1 squared. Okay, so 1 squared is a bit of an easy one to simplify. 1 times 1 is equal to 1. So it's 4 times 3.14 times 1. And now I'm multiplying. Anything times 1 is equal to itself. So 4 times 3.14 is 12.56. 12.56 square inches is the surface area of the green ball. And now let's do it again with each of the other balls, one after the other. So I'll erase this. I'll leave the green one right there, and I'll do the orange one, the orange street hockey ball. I will just say area of orange is equal to 4 times 3.14, but the radius of the orange ball is a little bigger. It's actually 1.25 inches. Okay, time for me to get my calculator. 1.25, and I'm also keeping an eye on the time. 1.25 squared, 1.5625. I'll write it 4 times 3.14 times 1.5625. But now I'm multiplying, it's all multiplying now. I've done the exponent in the formula following the order of operations, so now I'm just multiplying. I'm going to multiply it all out at once. I already have 1.565 in here, times 4 times 3.14, and I'm getting 19.625 square inches. Area, it's squared. Okay, so a little bigger, but that's what we expected because the radius is a little bigger. Let's do the third one. So I'll erase the green one, and the third one was the lawn bowling ball. So I'll call it area lawn. We know what I mean. And it is, again, 4 times pi times the radius squared, but the radius of the lawn bowling ball is 2 inches. Well, that's another easy one. 2 squared is 4. 4 times 3.14 times 4. I don't think I want to try to do this in my head. I'm going to use my calculator. 4 times 3.14 times 4 equals 50.24 square inches. It gets bigger fast, but of course the radius got quite a bit bigger, so then we see that the surface area gets quite a bit bigger and we're not surprised. Let's do the soccer ball, and then we'll do the basketball, and then we'll be done. I'm going to leave the lawn ball here for now. Let's move on to the soccer ball. Now, I actually had to go online to find out exactly what is the radius supposed to be of a soccer ball and a basketball. And it depends, because there are different sizes. So there are, for instance, basketballs that are a little bit smaller than regulation size that are used by kids. And same thing with soccer balls. You have your size 5, size 4, etc. So the radius that I decided to go with for my soccer ball, surface area of the soccer ball, is going to be 4 times 3.14, and the radius is, where did I write it? 4.5 inches. So 4.5 squared. Follow order of operations. I'm not multiplying yet. I want to know what 4.5 squared is. And of course it is going to be 20.25, isn't it? But I'm going to make sure. Yes, 20.25 times 4 times pi, 254.34. It gets bigger fast. Square inches. Okay, only one left to do for all of these spheres. Let's do the basketball. The basketball is just a little bit bigger. It looks quite a bit bigger, but it's actually officially just a little bit bigger than the soccer ball. Area basket is equal to, more chalk please, I'm running out of this piece of chalk, 4 times pi, 5-inch radius. Another one easy to calculate, 5 squared is 25, times 4 is 100, times, oh, it's kind of easy to do this one in our heads. 314 square inches is going to be the surface area of the basketball. And it gets bigger. Doesn't get that much bigger because let's face it, 5 isn't that much bigger than 4.5. So doing this formula with a bunch of different size radius is really all the variety that you get with the sphere. The sphere is interesting because all it gives you as a measurement that you can do calculations with is the radius. Of course, that means it also has a diameter. So the 4.5-inch radius soccer ball has a diameter of 9 inches. And we already know how to do that because we did that with the circle. And of course, therefore, the soccer ball, all of these balls, also have a circumference. So if I were to dip it in paint and then start rolling it across the driveway, it would make a line, and that would be the whole circumference going around until it got to the starting point again, and then it would continue drawing that line. It depends on whether I roll it up the driveway or down the driveway, I guess. Okay, so we have covered the sphere quite a bit. But like I said, there's only so much that I can do with the sphere for now. We're not covering volume yet in this lesson, so we will revisit the sphere when we get to doing volume. But the radius is the only thing that keeps changing as I use this formula over and over again. And all the radius is doing is getting larger or getting smaller, and it's giving you surface areas that are proportional to the size to the length of the radius. Kind of makes sense. Okay, next thing I want to do is get back to these rectangular prisms. And I want to invent an object that I'm not going to make it a cube. The cube is very straightforward. I think we need to get into some more rectangular prism geometry. So boxes. Boxes, you can have a box with no top. You can even have a box with no bottom, I guess. But let's talk about boxes that are rectangular prisms where you have a top, you have a bottom, you have cardboard on all of the faces of the box. So we therefore, if we calculate the surface area of a box, we're calculating the area of cardboard that we would need to make that box. And that's kind of interesting, because if you look at the way cardboard boxes are made, you often can see evidence that they were sort of folded together from something that looks like a net drawing. That's kind of interesting in itself. Okay, so how about a box? I think I want to draw a net drawing of my box. I'm going to make a cardboard box, and it's going to have one side length is going to be 1 foot. So let's start by just drawing a line that is 1 foot. There, 1 foot. Okay, but I don't want to make all of the side lengths 1 foot. It would be a cubical box, which could happen. But I want to make this more interesting. So I'm going to make a perpendicular side that's not going to be a foot. I'm going to make it 8 inches. So basically I'm just drawing a rectangle, aren't I? That's what I'm doing. I'm drawing a rectangle with a base of 8 inches and a height of 1 foot. But the thing is, I want to be able to make a whole box out of this, so I want to keep going. I'm going to draw another rectangle adjacent to this one, and I'll do it like this. And I'm going all the way to 16 now. And I'm doing the same thing up here. So I'm drawing a second rectangle the same size as the first. And that means this is going to be a foot, and look, it is. We're putting together a net. Okay, I'm going to put another one over here. Okay, I'll do it like this. Go to 16 again. And this is kind of fun. Drawing nets is fun. I'm not going to be able to get a big pair of scissors and cut the net out of the chalkboard wall and make a cool chalkboard right prism, because that would ruin the chalkboard wall. I won't do that. Okay, we have 3 adjacent rectangles. All of them are the same size. I can say, okay, this is 8 inches. So I'll show that. And I think, I have a problem that when I draw another, I have a problem that I don't have. So I'm going to continue. Okay, another adjacent rectangle over here. We have 4 of them. See, I didn't leave enough room to put the 5th and 6th. Now wait, I have to figure out what shape is it that I would be drawing up here. Maybe I do have enough room. I don't have enough room for an 8-inch by 12-inch rectangle here, but I don't need 12-inch. If we imagine folding, we're folding along these lines, like we did with my paper net, and what shape is going to be made when these 4 top sides are formed? They're going to be a square. So therefore, I don't need to make this piece up here 12 inches. I just need it to be 8 inches. Let's try that. 8 inches. 8 inches up there. This is also going to be 8 inches, so we're not surprised to see that it is. So that's a square. So this particular rectangular prism, it's going to have these 4 rectangles that are equal to each other, but it's going to have a square up here. I need another square on this side. Does the square have to be right down here? Or could I put the square there? That's another interesting thing that happens with nets. Okay, I'm going to do it this way so that I can see that I'm extending this line. So I'm going to 13, doing it again over here. Not bad, not bad. Let's connect these. So isn't that interesting? Now, if I were to fold all of this together, I would need those tabs. Of course, I'm not going to get giant scissors and do that. But if I were to put tabs, I have various places where I can put tabs. But the interesting question, I guess, is why did I put this square over here instead of right there? And what about, wait, could I have put it here? Could I have put it here? Could I have put it up here so that it covered part of the word geometry? No. So when you're building a net, part of the challenge of doing the drawing correctly is actually best tested by cutting it out and folding it together. And if you make a mistake, what'll happen is you'll be able to fold most of the faces together into the shape that you planned, but one of the faces, instead of covering the last covering that last space that you need it to, instead it's sort of overlapping with one of the other sides. You can make a mistake when you make a net drawing. And then you have this issue that there can be a whole lot of different strategies that different students could use to draw nets of the same thing. So if everyone wants to do a net of the one I just did, want to finish labeling it, if everyone wants to draw a net of the box that this would fold together to form, there are different strategies that work. I can put this square on any of these 4 spots, above any of these 4 rectangles, and I can put this square below any of these 4 rectangles. And I would still, once they're all folded together, I would still be able to get the 2 squares to fold over and make 2 opposite faces. Which, the way I'm drawing this, I kind of picture those as being the top and the bottom. But of course, like anything, any 3-dimensional shape, okay, right now, this triangle, let me see, I put some pencil marks on it, which is hard to do without squishing it, but there, I drew some pencil marks on it. Can I get them? Yes, they show in the camera. Okay, so right now the pencil is on the bottom, but of course I can just tip that over anytime I want and have another side on the bottom. So we can take this box that we're drawing here and we can tip it over so that instead of one of the squares being on the bottom, one of the rectangles is on the bottom. And it's still a rectangular prism, and it's still the same rectangular prism. Interesting. This can be called a square-based rectangular prism, and it's actually quite useful. We see a lot of square-based rectangular prisms. It's kind of interesting because it's in between this type of rectangular prism where you have 3 different areas and the cube where you only have 1 area. This one only has 2 areas. It has the area of the squares and the area of these rectangles. We may as well finish this off by calculating the surface area of this thing. So interesting, we did a 2-dimensional drawing of a 3-dimensional object. We don't have the object. We can't see the object right now. We can see this 2-dimensional drawing, the net of it, but we are able to still visualize what the 3-dimensional object would look like, and that's the usefulness of the math we're doing right now. And we can calculate the surface area of that object. So if it's a cardboard box and I don't have any tabs, I'm not going to worry about the area of the cardboard for those little tabs. If I'm just able to fold this together nicely and it makes a cardboard box, what area of cardboard would it take to make that box? So the area is going to be, I'm going off camera, but my chalk won't, the area of a rectangle, which is base times height, and it's going to be, I'll call it 8 times 12, which is 96 square inches. But there are 4 rectangles like that, so I'm going to multiply by 4, which is going to be 384, yes, square inches. But Doug has learned his lesson, so he's going to get his calculator and double check. 96 times 4. Yes, 384 square inches, but we're not finished. We have found the area of these 4 pieces of cardboard, but we need the area of these 2. Now those are square. I can do the area of a square formula, which is side length squared, and it's going to be 8 squared, which is 64 square inches. And I multiply that by 2 because there are only 2 of the squares. I need to switch to a new chalk folder or get a new piece of chalk for it. So I'm going to do that. I don't know where I put all my chalk holders. There's one over there on the computer table. But now I will have enough chalk for the rest of this lesson. Times 2 equals 128 square inches. Okay, so we add 128 and 384, and we're going to have the surface area of this cardboard box that we visualized. But we also could just use the area of our rectangle formula for these squares if we really wanted to. Let me do that over here. Area equals length times, not base times height, which is, in this case, 8 times 8. So yes, of course, it's the same answer. 64 square inches times 2 equals 128 square inches. Okay, either way, whether we want to use the area of a square formula or the area of a rectangle formula for those 2 squares, we are adding 384 and 128. 2, carry the 1, 5, and 4. 452 square inches is the surface area of this box. That's cool. Now, we can do this over and over again with different rectangular prisms. And I guess I didn't make the net drawing as challenging as I could have because of the fact that I chose to have a square. But I don't have to do that. Do I dare to try to do a net drawing? Now, I have a good model, a net drawing where there are 3 different areas, kind of like this staple box. I could do a net drawing of this staple box, but that would be an awfully small drawing. How about if I do a net drawing of a giant box of staples that is going to be very much like this one, but I'll multiply all the dimensions by 5. Okay, that's what I'm going to do. So I'm just improvising. A cool thing to do with this 3-dimensional geometry that makes me use all of these tools that I've been learning. And of course, in this case, it's going to be a bunch of areas of the rectangle formulas, but that's no problem. They're useful. We're going to be doing those a lot anyway. I'm going to take a quick sip of my fizzy water. It's watermelon flavor. Okay, I was talking nonstop for quite a while before I finally got that sip of fizzy water. I like this drawing, I'm proud of it, but I have to erase it. So let's make another one. We're going to make a net drawing of a box that has all the dimensions 5 times whatever the dimensions are of that staple box. And I have to be careful that I don't accidentally make the drawing cross over my geometry label, which has been there for quite a while, and I just don't want to erase it before it really needs to be erased because we're still covering geometry. And geometry lessons have been going on for a while now. It's a good thing geometry is so much fun. Okay, so 5 times these dimensions. Let's start by measuring the longest length of this thing. The length of the longest side on this thing. Oh, that's magnetic, and the ruler is, ooh. It's trying to pick up the box because of all the staples in the box. It's not quite strong enough to do it. Okay, so let's measure that. That is 4.5 inches. So I'm going to do a little calculations way over here. 4.5, and I said I was going to make everything 5 times bigger. So 4.5 times 5 is 22.5. I need to draw, 22.5. My net drawing is going to be huge. I'm changing my mind. I'm not multiplying it by 5, I'm multiplying it by 3. instead of erasing with my finger, that just makes a horrible smudge. Let's get the proper eraser cloth. Okay, let's multiply everything by 3 instead of by 5. I don't want my net drawing to be too big. Now that's 13.5 inches. Okay, so it's actually bigger than the 12 inch, which is the longest side on the previous drawing. I'm going to try not to put it up too high. I'm going to move it down a little bit. Yeah, that everything should fit. So I want to draw a 13.5 inch line. Now I also want it to be kind of, still look like a staple box, where this is supposed to be, what I have on the bottom is supposed to be the bottom of this staple box. So instead of drawing the 13.5 inches this way, I'm going to draw it horizontally. And that should make everything fit a little better. We'll see, I hope. 13.5 inches. This is fun. I'm going to be honest about that. Okay, what is the second longest dimension of this thing? That is this. That's along here. Okay, so this is a lot shorter. 1.75. I will call that 1.75 inches. Times 3 equals 5.25. I have to draw a line that's 5.25 inches long. That's not so bad. This is going to fit rather easily. And that line, I can draw it perpendicular to the first one, so I will. 5.25 inches. There. 5.25 inches. There. Okay, so I've drawn my first rectangle. Trying to visualize, okay, which face did I just do? What I just drew was the top. That was the top or the bottom, because that's the largest face this has. The third dimension that I have to measure still is the shortest one. So, I'm starting to visualize what it is I have to do in this drawing. Okay, so that 5.25 isn't going to repeat down here or up there. Not right away. So I have to do my third measurement to know what I am drawing next. My third measurement is quite small. I'm going to call it 1.4 inches. 1.4 times 3, that's 4.2. So instead of drawing another 5.25 inch line, I'm drawing a 4.2 inch line. Let's see what it looks like. 4.2, it's about like that. 4.2, where is it? It's about like that. And we can see we have drawn a rectangle that's smaller. So we're drawing another 13.5 inch line. So that's interesting. These two adjacent faces have to be different sizes, and it's sort of, I'm discovering this as I go, but at the same time I'm looking at this, I'm thinking, yeah, of course, there's the top, there's the next one. It's not as big a rectangle. So what I need is another 13.5 by 5.25 inch down here. That's where I'm choosing to put it. So 5.25 again. 5.25 again, and then the 13.5 again. And it's starting to get hard for me to draw. See, I'm struggling here a little bit. There. Because I'm getting too low on the chalkboard wall. So the next face, which is going to be another one of these, is I'm going to put it up here. So that was 4.2. 4.2, and another 13.5. Yeah, I don't know if it shows that well on camera. I think though, when I look at the video screen, you can see that this top one and this third one are the same size, and that they're smaller than this second one and fourth one. Now I have to do the remaining, the end pieces. The end pieces are going to be 5.25 by 4.2. So, I actually have choices about how I do that. I'm going to just start by doing one right here. It's already got a 5.25, so I have to go 4.2 over here. 4.2, let's see how that looks. That's in the way. 4.2. This is fun. This is more fun than I thought it was going to be, actually. It's more fun doing it on the chalkboard than it is doing it on the paper. Maybe it's just because I'm not alone now. I did it on paper before. I was sitting all alone at the dining room table. Okay, now I could do another one this size here. Let me try and, I'm visualizing in my head right now, folding all this together. No, I'm not getting a giant pair of scissors, but I'm visualizing folding it together. Obviously, I can fold these four into a nice box shape, and this is going to close off that box very nicely. So if I do another one like this over here, it's going to work. But I'm just asking myself, what if I wanted to put it here instead? So I'm visualizing that. Yeah, it's going to work. So this, I had already the 5.25, so I drew out the 4.2s. Here I already have the 4.2s, so I'm drawing out 5.25s. I am actually kind of going out of my way to make this more challenging, but I just find it very interesting, so I just want to do it. So 5.25, and then over here as well, 5.25. Interesting. I've done net drawings before, but I've never actually done this thing that I'm doing right now, to choose to make it more challenging in this way. But yes, I believe this net drawing I folded together would correctly make a big staple box for great big staples, which would be similar. I think similar is the right word, but I guess I should say would be proportional to this one. So we multiplied each of the side lengths by 3. So all the dimensions are 3 times as long. Does that mean that the surface area is going to be 3 times as big? No, actually, it doesn't mean that. But that doesn't matter. We're still able to find the surface area. When I find the surface area of this, it's not going to be and I guess I'm pointing out something really obvious. Maybe all the students are listening and thinking, well, obviously that's obvious. The surface area of this all folded out into a net is going to be much smaller than the surface area of this net that's on the chalkboard wall. So yeah, that makes sense. So I can find the surface area of both, and I guess I have just about enough time left in this lesson to do that, depending on whether I decide I want to do something else. So I'm looking at what else there is in the lesson. You know, this type of geometry could be many lessons. Just thinking of all the different pyramids. You could do a whole hour on pyramids and not cover all the different things that you can do with pyramids. All of the different prisms that are like the pentagonal prism, etc. There's so much that can be done. But I find it's extremely interesting just to explore the rectangular prism in the way that we've been doing so much of in this lesson. And I'm looking at what else we have. I didn't really ever get into the square-based pyramid, which is an interesting shape. But we did cover the spheres. So I think I'm good. I'm going to find both areas, and I'll keep everything on the chalkboard wall while I do it so that we can compare. So the area of this, the surface area of this, is going to be 13.5 times 5.25, but there are going to be 2 faces. That's going to be this one, the one that I'm shading right now, but there are 2 because there's this one as well. So I'm going to end up doubling that, but I don't want to make it look like it's a formula. I'm just going to do the area of the rectangle, and then I'll double it later. So on 13.5 times 5.25 equals 70.875. But 2 times that, so I'll just say times 2 and I'll erase this, equals 141 point something times 2, 141.75. I won't write the unit of measure, I'll just do that at the end, because I also have to do 13.5 times 4.2. 56.7 times 2 equals 113.4 times 2 equals, yes, Okay, and then finally it's these two little ones, which are the same even though I drew them so they look different. They're still both 4.2 by 5.25 inch rectangles. So even though I have to draw really low where when handwriting is messier, I just want to do it all here. So 4.2 times 5.125, no, 5.25 equals 4.2 times 5.25 equals 22.05 times 2 equals 44.1. Okay, I didn't really leave enough room for the final answer, so I'm going to erase this. What I'm going to do is add these together. 141.75 plus, need more chalk, 113.4 plus 44.1. Okay, 5, well, that's a 2 carry the 1, so 9, yes, and then I have to make sure I didn't draw this very neatly. 4 plus 1 is not another 9, and then there's this 1 plus 1 is 2. Let me make sure by using the calculator because this is messy. 141.75 plus 113.4 plus 44.1 equals 299.25 square inches. Okay, let's do this. Do this one. That's these smaller amounts. So it's 4.5 times 1.75 7.875 times 2 equals 15 point something, 15.75. Then 4.5 times 1.4 equals 4.5 times 1.4 equals 6.3 times 2 equals 12.6. Okay, I'm getting down into the messy handwriting territory. Finally, it's 1.75 times 1.4. Yes, 1.75 times 1.4. 1.75 times 1.4. 2.45 times 2. Is this fitting in the rectangle? It's hard to see. Yes, it's fitting. Equals 4.9. Now I'm going to add them together. I'll do it up here. So 15.75 plus 12.6 plus 4.9 equals 15.75 plus 12.6 plus 4.9 equals 33.25. Inches squared. And we're pretty much out of time. I'm going to say goodbye soon. I'm going to let the dog say goodbye. Oh, her tail just started wagging. Somehow she knows. But I just wanted to point out one interesting little thing that I noticed. It was something about this number and this number that triggered something, and I was curious, and I went into my calculator. Notice how to get the little staple box to be big enough for my chalkboard wall giant staple box, I multiplied everything by 3. But then we look at the total surface area of the little plastic staple box, 33.25 inches, and multiplying that by 3 is not going to give us 299.25. But I'll tell you one thing that's kind of cool. Where will I write it? I'll write it right here. 33.25 times 9. I just did it in the calculator. I'm not making this up. 33.25 times 9 happens to equal exactly 299.25. I don't know, I'll just put a nice big bracket around this just to point out that something interesting has happened there. And it's the sort of interesting thing that you discover when you play around with math, because I have to admit, I was most of the way through this lesson plan and I just suddenly decided I felt like doing this. And I decided, suddenly, it was improvised. I suddenly decided, hey, how about I actually use this one, but I'll make it bigger. And then this interesting little thing just happens by itself, almost as if there's math there that has something to do with area and proportion and similarity, and that is waiting to be discovered. So I guess our geometry careers are still near their beginning, and there is some interesting things that are left to be discovered. Why would that times 9, not times 3, why would multiplying it by 9, oh, it's just worth thinking about. So with that, I will say goodbye. Thank you very much for being here. It was fun as usual. The hour flies by as usual. And this dog has already had her supper, but she's still all excited because the class is coming to an end. Maybe she thinks she's going to get another supper. I have bad news for you, little Miss Sleek. Okay, thank you very much for being here, and I will see you next time.